Alright, this problem requires that we find the tensions T1 and T2 in two cables that are tied at a knot with a 70 kilogram mass hanging straight down from it. And so the conditions for equilibrium, or translational equilibrium at least, is that the three forces acting on this point in space right here add up to 0. Alright, so there's a rotational requirement for equilibrium, but it doesn't apply in this case because we're applying the three forces to a point in space. And so the tension cable T1 is 15 degrees to the horizontal, and so we're going to apply a Cartesian coordinate system to our picture, and cable T2 is 55 degrees to the horizontal. And so what I'm going to do is decompose the vectors into x and y components, and the resultant vector of the three forces as a requirement for equilibrium must be 0. And so the x components have to add up to 0, so T2 cosine 55 degrees minus T1 cosine 15 degrees is equal to 0. So these two are the x components. So this component and this component. Alright, so the y components, there are actually three components in the y direction because there are one from T1 and T2, tension 1, tension 2, and also this one right here. Alright, so the y components are going to be T2 sine 55 plus T1 sine 15 degrees minus 70 times the local gravity equals 0. Alright, so these components right here, here's the y component for this one, y component, and this is all purely y. So this one is this one right here. Alright, so we have a system of equations. We have two equations and two unknowns. So we have to apply methods for systems of equations. First thing we have to do is to evaluate the cosines and sines of 15 and 55 degrees. Simplify this, move it over to the right. So we're going to get 0.574 T2 minus 0.966 T1 equals 0. The y equation gives me 0.819 T2 plus 0.259 T1 equals 686. So this is equal to 686, and I moved it over to the right, giving me this right here. Alright, so now I have it in what looks like a traditional matrix form or a system of equations form, where the two unknowns, like unknowns, are lined up, nice and neat, and we're ready to solve by elimination. You could solve by substitution or elimination, it's your choice, and I'm going to do elimination. So I also prefer to add equations. Whenever I'm doing elimination, I prefer to add negative and positive coefficients because I think it leads to fewer mistakes. And so what I'm going to do is force these two coefficients to match so that when I add them, they're going to cancel out. Alright, so I'm going to multiply the top equation by 2.259 and the bottom equation by 0.966. So that will ensure this times this is the same as this times this. I get the same number with opposite signs. Alright, so it's a very simple strategy. This is going to give me 0.142 T2 minus 0.250 T1 equals 0. Draw a line. Okay, and then the second equation gives me 0.791 T2 plus 0.250 T1 equals 662.7. So the key is that you multiply whatever you choose as multipliers out here, you multiply the entire equation. One of the first mistakes that young people make is they fail to multiply all the way across. They'll stop here or here and forget about the last term or something along those lines. So just make sure you multiply all the way across. Alright, so now we're ready to add the two equations. So as a result of what we've done, these two terms are going to cancel each other out. And we're going to solve for T2 first. Okay, so this gives me 0.933 T2 equals 662.7, and then I can divide and solve for T2. So T2 is 710.3. Alright, and now we need to take this value and plug it back into one of the original equations. It really doesn't matter which equation, because we're solving for a point in space where they're going to share the same T2 and T1. So either equation can work. I'm going to choose the simpler one simply because this one contains a 0. And so 0.574 times 710.3 minus 0.966 T1 equals 0. So subtract this, or add this, move it to the right, and then divide both sides by 0.966, and T1 is equal to 422. So with this force, this tension, equilibrium is met in the system, and the knot, it does not move because the sum of the forces acting on the knot are 0.